All right, so here we are in section 2.4. And 2.4 is a very unique section of our book. It's the most theory-focused section that we cover in this class. And when I say theory, what I mean is a part of math where our focus is on proving things as opposed to calculating things. So the goal here is to prove rigorously different facts about limits and things like that. Even though we're going to use this definition to evaluate some limits, it does not make evaluating limits any easier. In fact, it makes it a whole lot harder. But that's actually not the point. The point of this precise definition of a limit that we're talking about in 2.4 is not really to use to evaluate any given limit that you're given. It's to put the concept of a limit on rigorous footing. What this means is that we're going to be defining the limit in a mathematically precise way. Now, the reason we need to do this is because in section 2.2, we gave what we called the intuitive definition of the limit. And the reason for the word intuitive is because it had some vague terms in there. Specifically, we used these terms in that definition: arbitrarily close and sufficiently close. We never gave a mathematical definition about what it means for two numbers to be close. We sort of just relied on the fact that that's an intuitive idea and relatively easy to understand. Now, if you pursue math beyond this course, you will learn once you get to university level upper division math that you're not allowed to assume anything is obvious in math. You're not allowed to just assume 1 + 1 = 2 because it feels obvious. You actually have to prove everything. That's what makes math powerful, is that we can prove things with a higher standard of proof than we do in any other discipline. Much, much higher standard of proof than in any of the sciences and anything like that. But it takes a long time to sort of wrap your mind around what some of that stuff looks like. So I'm going to go ahead and move forward with this now that I've given my little introduction, and we'll kind of see what we mean by these terms: arbitrarily close and sufficiently close. So let's just look at the word close for a moment. Close, the idea of close is related to the concept of distance. What do we mean when we talk about the distance between two numbers? Well, what we mean is how far apart two numbers are on a number line. So let's suppose that we have two real numbers, x and y. Both of those numbers can be put onto a number line. And the distance between two numbers on a number line can be found using this little expression: the absolute value of x minus y. And sometimes this expression is called absolute deviation, but what it means is the distance between two numbers. Now, to see why this is the case, here's an example of a number line where we're calculating distance between two numbers. What is the distance between -3 and 2? Well, that's easy enough to find. Actually, I think I did 3 and 2 first, so let's look at this one. What's the distance between 2 and 3? Obviously 1 unit. It's 1 unit apart. I can see that right here. But if I wanted a formula that would give that to me, I could use that thing up there: x minus y in absolute value. The tricky thing is which one of these numbers is x and which one is y? Well, it turns out it doesn't matter. You get the same result regardless of which one you call x and which one you call y. And to see why, do it either way. What is the absolute value of 3 minus 2? 3 minus 2 is 1. The absolute value of 1 is 1. If I reverse the order of those numbers and do 2 minus 3 instead of 3 minus 2, all I get is the opposite of what I got here. Instead of 1, I get -1. But since I'm taking an absolute value, it still comes out to +1 anyways. So the absolute value is what makes it so I don't have to worry about which number is subtracting from which number. Similarly, I could do the same thing here. What's the distance between -3 and 2? Well, I could count the jumps if I wanted to and see that it's 5 units, or I could just use this formula. The absolute value of one number minus the other one, absolute value of -3 minus 2, would come out to 5. So I could say that the distance between -3 and 2 is 5. Okay? And so what that means for us is when we're talking about closeness, when we talk about two numbers being close together, another way of saying that is we want this absolute deviation, or this absolute value of the difference between those two numbers, to be small. These two numbers are close together if the distance between them is small, okay? So let's take a look at an actual limit now, one that's easy to evaluate based on what we've done in previous sections now, and see if we can investigate this idea a little bit more. So here I'm looking at the limit as x approaches 1 of 2x plus 3, which we could very easily verify is equal to 5. Notice this is one of those examples where I could use direct substitution. Okay, so if we went to our intuitive definition of the limit to explain what this means, we could say that the values of 2x plus 3, this expression, can be made arbitrarily close to 5 as x is brought sufficiently close to 1. And what we mean by arbitrarily close here is that this expression can be made as close to 5 as we wish. Once we decide on how close this expression is to get to 5, we could then figure out how close x needs to be to 1 to make sure that that happens. Okay, that's why we use the term arbitrarily here, but sufficiently here. And we'll make more sense of that with an example. So I kind of explained that here, but let's suppose that when we say, come back here, when we say that we want to make 2x plus 3 arbitrarily close to 5, let's be a little bit more specific and say that we want to make 2x plus 3, which I'm going to be calling f of x for reference down here. We would like for this expression to be within 0.1 units of 5. Within means 0.1 units or less, or in this case, we're just going to say less than 0.1 units. So I would like my function, 2x plus 3, which is f of x, to be less than 0.1 units away from 5. Okay, well, we've defined f of x to be equal to 2x plus 3, so I can simplify this expression here in the absolute values. The absolute value of f of x is equal to 2x plus 3 minus 5. 3 minus 5 is negative 2, so I have the absolute value of 2x minus 2. I could factor a 2 out of each of these, giving me 2 times x minus 1. Now there is a property of absolute values which says that if you have the absolute value of a product of two numbers, or expressions, or whatever they happen to be, that is always equal to the product of the absolute values of those. So I have a product, 2 times this expression. I can write that as the product of the absolute values of 2 in that expression. 2 has an absolute value of 2, so this is most simply written this way. Now, what was the point of going through all of that work? Well, again, we said that we want f of x to be within 0.1 units of 5, but the sufficiently close part of our intuitive definition is basically saying how close does x need to be made to 1 in order for this to be true. Okay, so remember, x is approaching 1, and when x is approaching 1, we're expecting f of x to approach 5. So how close does x need to be made to 1 in order for f of x to be within 0.1 units of 5? And remember, the distance between x and 1 is given by this expression, the absolute value of x minus 1. Well, notice that after doing all of the simplification here, I ended up with an expression that has an absolute value of x minus 1 in it. So I can replace this absolute value here with this equivalent one right here to get this inequality. 2 times the absolute value of x minus 1 is less than 0.1. And I could solve for that absolute value by dividing both sides by 2, giving me this. The absolute value of x minus 1 is less than 0.05. Okay? So what this means is if I want f of x to be within 0.1 units of 5, then I need to make sure I'm using values of x that are within 0.05 units of 1. Okay? This is a tricky thing to wrap your mind around the first time you see it, but this is kind of what's going on behind the scenes of a limit. Okay? Another way of stating what we just said as an if-then statement, I could say this. If the absolute value of x minus 1 is greater than 0, I'll explain that part in a second because we didn't see that showing up there, and less than 0.05, so this is the part of the inequality that we're seeing here, then the absolute value of f of x minus 5 will be less than 0.1. Now the reason I'm saying this, greater than 0, what would happen if this absolute value equaled 0? Well, that could only happen if x was equal to 1, because notice then I would have 1 minus 1, which is 0. And it's important to note that when we're talking about limits, I'll go back to this page here. When we're talking about limits, as we have said over and over again, x is approaching 1 without ever having to equal 1. Okay, because we're looking at the behavior of this function as x gets close to 1, which may actually be different, depending on the function here, than what happens when x is exactly equal to 1. So we do not want to have to account for the case where x is equal to 1, and by putting this restriction on here, making this greater than 0, that's ensuring that x is not equal to 1. That's the only purpose behind that greater than 0 there. Okay? So notice that the number that I got here was ultimately dependent on this number here. This number I can think of as like a threshold. I set a threshold to begin with. I want to bring f of x within some number of units of the number 5. And with that assumption, we went through some work to show that x would have to be brought within 0.05 units of 1 to ensure that this happens. But I could choose different thresholds. Remember, we want to be able to make f of x arbitrarily close to 5, meaning I should be able to make f of x as close to 5 as I want. Or in other words, I should be able to make this number as small as I want. And no matter how small it is, I should always be able to find another number that I could put here, which will guarantee that this is true. Okay, so let's use an example to investigate that with this same limit. Using f of x as we've defined it up above, f of x equals 2x plus 3, I want to determine the value of delta. This is the Greek letter delta, a lowercase delta, that guarantees that the absolute value of f of x minus 5 is less than 0.001 anytime the absolute value of x minus 1 is greater than 0 or less than that delta that we decide on. So in other words, this delta is whatever number belongs here to ensure that this happens. Okay? Now we've already gone through all of the simplification in this work right here. So basically, if I wrote this, f of x minus 5 is less than 0.001 would means that, remember that's simplified down to this, 2 times the absolute value of x minus 1. And that's the same, this is equivalent to this, so we would want this to be less than 0.001. Dividing both sides of this by 2, so the absolute value of x minus 1 would be less than, dividing by 2 gives me 0.0005. Okay? Therefore, this little symbol right here, these 3 dots in a triangle, means therefore. Set delta equal to 0.0005. Okay? The whole point of that is that I made this threshold, this number, much smaller than it was up here, or again up here. But it doesn't matter that I made it smaller, I was still able to find another number that could be put here to guarantee that f of x could be brought that close to 5. And that's giving us more evidence that the limit in question here should be 5. Okay? All right, so let's see if we can turn this into an actual definition that's useful. This is the precise definition of a limit. And I'm just going to warn you, this is a notoriously tricky concept for beginning calculus students to wrap their mind around. So you kind of need to read it and sit with it for a while to really try and understand what it's talking about. So here's our definition. Let f be a function that's defined on some open interval containing the number a, okay, except possibly at a itself. Then we can say that the limit of f of x as x approaches a is L, and write this notation. So far it's looking like the same definition that we gave previously, our intuitive definition. Here's where it starts to look different. We can say that this limit is equal to L if for every number epsilon, that's the Greek number epsilon, greater than 0, so epsilon is any positive number, there exists another positive number delta, such that if the absolute value of x minus a is greater than 0 and less than delta, then the absolute value of f of x minus L is less than epsilon. So that's a lot to unpack. Let me just kind of talk about how this relates to what we already did. This epsilon right here represents the threshold I've been talking about. It represents how close we want f to be made to our limit L. Okay, so looking back, find, not that page, this page here. I don't know. Where did I put that if-then statement? Was it here? Yes, here, okay. So here is that if-then statement for our specific example. If 0 is less than absolute value of x minus 1, which is less than 0.05, then the absolute value of f of x minus 5 is less than 0.1. So comparing that to our precise definition here, this the number 1 is taking the role of A. Delta is 0.05. Notice the delta is the thing that we had to find once we decided what epsilon was. Epsilon in this case is 0.1. See where epsilon appears? That's the 0.1 here. 5 is the capital L. It's the limit, okay? So this is stating in more general terms what it means to prove, or what it means for a limit to exist and be equal to L. We did a couple of examples where we picked values for epsilon. We picked 0.1, in which case this delta needed to be 0.05. Then we picked 0.001 for epsilon, in which case this delta needed to be 0.0005. What this is saying is that if our limit that we stated at the very beginning, if the limit as x approaches 1 of 2x plus 3 is supposed to be equal to 5, then no matter what positive number I pick for epsilon, I should always be able to find a delta, some other positive number, such that when this is true, this is guaranteed to be true. Okay? So let's unpack this a little bit more, and then we'll actually look at some proofs and stuff in the next video. I want to investigate this inequality here before anything else. So grabbing this guy, what does this mean literally? The absolute value of f of x minus L is less than epsilon. We already stated that this means that the distance between f of x and L is less than this epsilon. When you see that epsilon in these proofs, you want to think of it as a very, very small positive number. Because even though it says for every number epsilon greater than 0, when we think of limits approaching things, we think of closeness, right? We think of this becoming small. So think of epsilon as a small number. In algebra, when you talk about absolute value inequalities, you show that when you have the absolute value of something, of an expression, which is less than some number, that's equivalent to this compound inequality. F of x minus L is between negative epsilon and positive epsilon. Or if I add an L to everything here, this could equivalently be written this way. F of x is greater than L minus epsilon, but less than L plus epsilon, which is another way of saying that f of x lies in this interval, the interval from L minus epsilon to L plus epsilon. Hopefully you're tracking with me okay here. Similarly, we could do a very similar thing with this inequality, starting with just this part of it. Forget about the 0 for a second, and show that this inequality is equivalent to saying that x is between a minus delta and a plus delta. This greater than 0 part here adds the condition that x is not equal to a. Okay, but that means that x lies in the interval a minus delta, a plus delta, again, provided that x is not equal to a specifically. Okay, so another way of stating the precise definition that we just talked about is this way. The limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0 such that if x is in this interval, then f of x is in that interval. Okay? Graphically speaking, this is what that looks like. So again, we decide on what epsilon should be. Once you choose epsilon, that's going to determine how big this interval here is. Okay, so we think of that as like a target. Notice that interval is centered at L, which is supposed to end up being our limit. Once we've decided on this interval, so deciding on epsilon, we then need to find a corresponding value of delta, which will determine the size of this interval where x lives. Once we have found that, if this limit exists, if the limit as x approaches a of f of x is equal to L, then no matter what point we choose in this interval, once we plug it into our function, the result should always land in this interval. We should never be able to find a point in here which can be plugged into f and give us a result that lands outside of it. We should always hit that target if this delta was found correctly. Okay? Here, graphically, is another way of looking at the same concept. So again, suppose we have some function f of x, and here's what the curve would look like if we graphed it, that red curve. And again, in this definition, this precise definition of a limit, the first thing that we do is decide on a positive number, epsilon, which determines an interval around L. Okay, so down here would be L minus epsilon, here's L plus epsilon, and so the interval L minus epsilon, L plus epsilon is right here on my y-axis. Okay, notice how that determines kind of this strip in the xy plane. And now let's suppose also here's A. What I need to do is determine a corresponding value of a corresponding positive number, which we're calling delta, which gives us some interval around A such that all of the points in that interval, when plugged into my function f of x, land within that strip. Okay, that's what that's saying. Notice if delta is made too large. What if I put delta out here? I widened that interval, right? Well, if that's the case, then some of the points in that interval are going to give me points on my curve that lie outside of that strip. So delta has to be made small enough so all of the points in here lie inside that strip. Okay? And because this is supposed to be possible, for every choice of epsilon, if I make epsilon super, super small, it's going to shrink down this blue strip, which means my corresponding delta will probably also need to be made smaller to make sure that the same thing applies. All of the points in this smaller interval will need to land in that strip. Okay? And as so this is kind of illustrating the idea behind a limit. As these points get as this delta gets smaller, shrinking this interval down, we should also have a shrinking interval here so that everything kind of collapses down to a point. Okay? I'm going to stop this video here. That's enough to chew on for now. We'll start looking at some actual examples and proofs in the next section.